And welcome back to Turdford channel. All right, so today's video is actually the fourth video in a set of rotational review problems that I've been working, and kind of sort of getting these like in terms of the AP exam and helping review and get you ready for the AP. This video itself is dedicated just really to one purpose, and that is centripetal acceleration. So today's video is a problem dealing with centripetal acceleration that we're looking at. So let's go straight in and start looking at the problem. So this problem starts out, a 44 kilogram child takes a ride on this Ferris wheel. Well, that puts us in this world of rotational motion, because you have to think of the motion of a Ferris wheel is obviously it's traveling in a circular motion. So it's giving us a little information here. It tells us that the mass of the child is 44 kilograms. Check. Takes a ride on a Ferris wheel that rotates, what does it say here? Four times each minute. Now, some people get confused by this, and they'll think it's giving you a angular displacement and a time, but it's really just a long-winded way. That's right, a textbook manufacturer would do that. A long-winded way of essentially coming back and telling you that your angular velocity is 4 RPM. And we can't go too far in this problem, because one of the things we've discussed before is we can't do math on this RPM. So before we go any farther in the problem, we need to change this to radians per second. And I've done this in older videos, but not in this newest series. So let's do that real quick. Let's do this conversion. 4 revolutions per minute. This is the exact same way you set up to convert, say, miles per hour. Their X, draw our line, and let's first take care of the revolutions. So remember, what is a full revolution around a circle in radians? Well, there's 2 pi radians for every 1 revolution. All right, but we're not done. We also need to take into account that per minute. And so we know that there's 60 seconds for every 1 minute. And if you want to go through and be like nitpicky with our crossing out, if you notice, the revolutions cancel and the minutes cancel, and so we're left with radians per second. So if we look, our math is essentially what? 8 pi divided by 60. Well, let's get that to decimal form in our calculator. So 8 pi divided by 60. It looks like 2/15 pi, but let's get that to number 0.42. So this is 0.42 rads per second. And if you're really using this for a review video, you should already work this problem faster than I can work it. Now, it gives me one more piece of information. It's trying to be a little tricky. It gives me the diameter of the Ferris wheel. Well, in these problems, what we're interested in is the radius. So we will not fall for your little trickery today. Thank you very much. So I think right off the bat, what's going to get somebody is look at the first question. What is the centripetal? Notice the centripetal acceleration of the child. What will trick somebody up a lot of times, and this problem doesn't say it, but it is implied in the question. A lot of times a problem like this will throw the word, it's traveling at a constant velocity, or it's traveling at a constant angular velocity, or the magnitude of the velocity remains constant. And what happens is you guys are so programmed to seeing constant velocity that gets you automatically set up for trick questions. So say, for example, you will see this constant velocity and you automatically go and write acceleration is equal to 0. Well, here's the thing, you're not totally wrong. The tangential acceleration, I don't like how I write that, so here, AT. Your tangential acceleration is 0 if you're actually referring to something traveling with a constant velocity. But what you've got to take into account for a second, let's do something. Let's think about let's think about David and Goliath for a second. Let's think about that sling. So as we get this set up, let's think about the sling. So we've got one point on one end where you've got David's hand holding the sling. That's probably the worst hand I've ever drawn in a video. And you've got this stone that's traversing a circular path, and that stone is in the sling. And what happens is David releases the sling at some point, and the stone flies out with this. And this is where we get this tangential velocity from. It flies out at this path tangential to the circle. And so what happens is you'll see constant velocity, and then you go right to thinking, aha, acceleration is equal to 0. But you've got to remember the foundation of what velocity is. Velocity is magnitude and direction. So when you think about it, what is a stone traveling in a circle doing, or any object traveling in a circle? I'm drawing the most crooked arrows I've ever drawn before, but anyway, that's not totally relevant. You got to remember what's true about acceleration. It's a change in magnitude and direction. So if we see this object, it's changing direction, so we do have an acceleration. And we could do some weird, ugly drawing, but my arrows are bad enough. But that acceleration is towards the center of the circle, and that's a centripetal acceleration. And i.e., you can also think of it like this: there's got to also be a centripetal force, because when you think about it, this object doesn't want to travel in a circle. It wants to travel in a straight line, which is why the second David were to release his sling, the stone would travel at this tangential path to the circle of which it was transversing. So that string is providing a force, a centripetal force, to keep the object moving in a circle. So there's kind of our foundation. So part 1 of this problem just says, find the centripetal acceleration of a child. Well, that's easy. Centripetal acceleration is nothing but, and we could derive the formula, but here, I'll even put the little t in there so I can be nitpicky with this. But centripetal acceleration is nothing but your tangential velocity squared divided by your radius. Now, I'm going to do something. We don't actually have a tangential velocity. We actually have an angular velocity. And so what I'm going to do is this. Let's do something. If you remember, we talked about in other videos, we've got an equation that says velocity is equal to r omega. So let's do something. Let's substitute that directly into that equation. We'd have r squared omega squared over r. The r and the square would cancel out. So we've got r omega squared. And so essentially all we've got to do is 9 meters times omega, which was, I think it was 0.42. Yep, it was 0.42. And 0.42 radians per second square. So let's kind of take a look at this, and we can do this roughly. Obviously, we can tell math-wise it's going to be a little under 5. So let's see what we get here. 0.42 times 9 equals 3.78. But what I want you to focus, so we've got our value, 3.78. Look at what your units would be. Your units would be a meter radian per second square. Now, that is a really weird, ugly looking unit. If you remember something we've talked about before, it's like this. Radians are like the phantom menace in physics and mathematics. Remember how you get radians. All you have to do is take an arc length, a circumference, if you will, around the circle, divide it by a radius, and that's how we get, that's where radians comes from. Wait a minute. So where did the radians come from? Arc length is in meters. Radius is in meters, which means the angle is really a unitless number, and we just generate this concept of the radian in here. So it's kind of like this phantom thing. It was never actually there. So if it was never there, that means, guess what we can do? We can let the radians just disappear, and our answer is 3.78 meters per second square. And this is what also drives students crazy, because it means sometimes the radians can just appear in the problem, just like they disappeared in that one. Now, a little trick question sometimes you'll be thrown at. You'll have an object that's traveling in a circle, And the problem will give you like some reference as to it is speeding up. So they will give you two accelerations. They'll give you a tangential acceleration, and then you've got to also know that you've got a centripetal acceleration. So if you're ever encounter that situation where you actually do have both accelerations, so you have like this linear acceleration and your centripetal acceleration, all you need to do is just take a Pythagorean on those and you'll have the total acceleration of the object. So all you've got to do, take a Pythagorean on the two accelerations, and then you'll know the total acceleration. So that's a little trick sometimes you'll see when working these problems. All right, let's do this. Let's go back and take a look at what force, magnitude, and direction is the seat exerted on the child at the lowest point in the ride. All right, this is kind of like one of those stock physics questions. It's a vertical circle question, and I'll summarize this for you. Whenever you're looking at something traveling, I'm going to draw a really big circle. Whenever something's traveling in a circle, what we can do is kind of take a look, and we can break it down. At the lowest part of the ride, you got to think about what's going on. At the lowest part of the ride, think about a string being slung in a vertical circle. Say you've got David's taking his stone and he's slinging it, this time in a vertical circle. Well, think about at the bottom. You've got some force. It might be a tension force or something like that. You've got some force directed up, and then you've got this force of gravity or weight, or in the end, mass times gravity, whatever you want to call it, directed down. The whole trick to doing centripetal force problems is just this, and I'll shoot one little bonus video on this because somebody actually just asked me today to do it. The big thing is this, and I'm going to go and write, for some reason, instead of writing MAC, I always write V square over R, because half the time that's just a quicker way. The goal in doing these problems is always figuring out what is the centripetal force. So what's holding this object in a circle is what it boils down to. So let's say it was like a rock traveling in a circle. Well, at the bottom of the circle, the tension is the only thing providing the centripetal force. The tension is what's directed up. So check this out. At the bottom of the circle, I may say something as easy as this. Tension minus the weight is equal to mv squared over r. Because think about it, the weight is not helping you. The weight is actually, in effect, working against you. But now look at the top of the circle. At the top of the circle, let's just say we still had like this rope or something slinging something. At the top of the circle, that rope, that tension, and yes, you notice I used F of T here and capital T here because I get so tired of people being hung up on their notations. But now look at this. The mg is directed down, which means at the top of the circle, the tension and the weight are both adding up to be the centripetal force. So they're working together. They're working combined. So hopefully you kind of understand this. Centripetal force is always as easy as what is equal to mv squared over r. What is your centripetal force? So if you've got forces present, what is actually aimed at the center of the circle? So at the top, both the tension and the weight are aimed at the center of the circle. At the bottom, the weight is working against you. So your tension's not only equal to the centripetal force, it's got to also be equal to the weight on there. Which is why if you're swinging on a vine like Tarzan, the most logical place for it to break is when you reach the bottom of the circle. That's where your tension is going to be the greatest. I.e., in terms of multiple choice questions, you should also be well versed now. If your tension is the greatest at the bottom because the weight is working against you, where would the tension then by proxy be the least? Well, obviously at the top because the weight is helping you at the top. And we'll talk about in a second what it is to actually be weightless. But now that I've talked for like 30 minutes, let's do something. Let's extend this. And let's go back and actually solve this problem. And so all it said, I'm all the way back up here now. What force, magnitude, and direction does the seat exert on the child at the lowest point of the ride? So at the lowest point of the ride, what we need to be thinking about is this. At the lowest point, of this ride, you've got on the Ferris wheel, you're going to have this weight pulling you down, this force of gravity, this weight, this mass times gravity. It's going to be pulling you down. The seat, hopefully, just like the seat your buttocks is planted in now, should be holding you up on the Ferris wheel. So as I go to work this problem, I know this. The force of the seat minus the mass times gravity is actually, it's working against me in terms of my centripetal force, is equal to mv squared over r. And we've got different ways of looking at this. Somebody might teach you and say, well, the seat has got to be equal to the centripetal force, the mv squared over r, plus the mg, and hopefully you'll notice they're teaching you the exact same thing I am. So it's irrelevant how you write that. So in the end, let's see if we can't work this out. Well, we already know what v squared over r is. Matter of fact, we've already calculated mv squared over r. We did it way up here. We already know, or excuse me, we haven't calculated that. Hey, well, you know, that's what we're doing now. We know this. We know the centripetal acceleration, so we know v squared over r. So let's see if we can't plug in some numbers and work this out. So the force of the seat at the bottom would be equal to 44 times v squared over r, which we've already calculated. That's our centripetal, 3.78. 3.78 plus 44 times 9.8. We could have factored the 44 out there and worked this problem, I guess, and done it. But anyway, let's see what we got here. So we got 44 times 3.78 plus, if you hear a rooster in the background watching a channel called the Turdferg channel, it should not surprise you to hear a random rooster in the background. And so our answer is 500 and let's round it 98 newtons. So at the bottom of the ride, the force of the seat is 598 newtons. Now, what this question asks for next is, what is the force? What is the force at the top of the ride? So what is the force at the top of the ride? So at the very top, we got to think about something. We've already discussed it, so you should already be working this problem. Now, at the top, my gut intuition, it's like David in the sling, slung in a vertical circle. I feel like the seat should be going down, and then we've also got this force of gravity going down. And we can just work with that assumption. However, you're going to see something a little bit odd in this problem as we work it out. So let's just go for that. Let's say, all right, I think the seat is helping the weight to hold this kid on the Ferris wheel. So let's just work this one out. Force of the seat, this time the only difference is, well, take a look. It's the exact same problem we just worked. What's going to be the only difference in this one? Yeah, exactly. Thank you, Mr. Rooster, for helping with that decision. It's the same problem we just worked. The only difference, use the replay button on my Casio. And we're going to change that plus to a minus. Now, something feels weird. We get like this negative 265 newtons. And you should be looking at this going, what is this negative sign for? Well, now you've got to think about something, and this negative is not directional in the case of what we think about like directions. Think about this kid. The Ferris wheel, it's not like the sling. This Ferris wheel, think about the cart, and for some reason I was looking at it, well, let's look at it kind of like a roller coaster even on top of the hill. So let's look at it like it was a roller coaster on top of the hill. So what's actually happening is, based on the speed that this is going, it's going so slow that in this problem, the seat is actually got a force directed in this direction. So the 265 newtons is actually almost a normal force, you could call it at this point, for this problem to work out. Now, there's a special situation, what's known as weightlessness. A lot of times, like with a roller coaster, it'll ask you, how fast could the roller coaster be going at the top before, well, the roller coaster went airborne at the top. By the way, their mathematics and roller coasters have a little aid in this department, just in case the math sucks. They're made to hold them to the tracks. But there is a special situation where you've got only gravity. So again, I don't know if you understood it. The reason why the force on the seat was lower this time, it's because this mass times gravity was more than enough force all on its own to keep the kid in the Ferris wheel traveling in a circle. Now, there is a special situation which we call apparent weightlessness. When you see apparent weightlessness, all you've got to do is this. At that point, you know, if you've ever topped the hill in a car or a roller coaster going a little fast, you've kind of felt a little vomit rise up in your stomach. What happened is this. You've reached like this magic situation where you're not feeling any apparent forces. You're not feeling the force of your seat anymore. And all you've got is the weight is equal to, the weight is actually just equal to what we see here. So the mass cancels out. The mass equals your centripetal force. Look at all you're left with. G times R square root equals velocity. And I'll tell you an extension of this problem, and I know this video's gotten too long, but we made so much stuff. A lot of times you'll see like a roller coaster problem, and it will ask you something about like, how fast should a roller coaster be going or something like that in order to try and not say it's this kind of the loop-de-loop question so that it doesn't fall off. Well, your velocity at the top of that roller coaster has got to be at least a minimum so that this situation is set up where your weight, your mg is, in other words, what's the centripetal force? The weight is the centripetal force. That has to be true. So what you can do, say for example, it was a problem where there was like a hill or something, and it asked you, how high should the hill be? Let's do H. How high should the hill be so that you can make this little rotation down here? Well, in that case, it's pretty simple. You take the potential energy of the roller coaster, you set it equal to kinetic energy. And you look at this and you're like, okay, well, that's kind of cool. And then you can back up a notch. And remember, we just did something. We saw that GR is equal to V squared. So look, we could substitute in the place of V squared. Look at this. MGH equals 1/2 M. The M's are going to cancel. V squared. And that's G times, look at this weird little bit of math. Mass cancels. G's cancel. So the height that the roller coaster descends from has to be 1/2 the radius of the loop to make this. So this is like an application of this tops and circles. And I say that because you would probably see something like that. All right, last question. What force does the seat exert on the child when the child is halfway between the top and the bottom? So let's do this real quick. So what is, and then this 20-minute video has got to come to an end because it's already just too long. But we've covered a tremendous amount of stuff here. So what about at the halfway point? And I'm not going to work this out all the way. You, by now, can do this problem. So think about at the halfway point what's going on. Your weight is actually straight down. Your mg is directed straight down. The centripetal force is directed towards the center of the circle. So now if you look at this problem and you're trying to find what the force of the seat is, you've got to kind of take into account, well, the seat, it's going to be in the opposite direction. But all you've got to do is take the Pythagorean, find your centripetal force. Remember, centripetal force is nothing but mv squared over r, which we've got all that information. plus the force due to gravity square, and that would give us the force of the seat at that location at that point. So that would be an easy little solution to try and figure out as well. But I'm going to do one more video kind of applying this and then turn you loose on it. All right, so 25 minutes. I got to say deuces later.